Okay, 15.3. 4, actually. So this is a chain rule. And we're going to continue with our discussion from last time about linear approximation or the tangent plane. And that's going to actually help us understand how the chain rule works in the multivariable setting. So the whole idea of the chain rule is going to be based on the simple situation where we have f of x comma y is a two-variable function, and then x and y both depend on another variable, which we'll call t. So x depends on t, and y depends on t. All right, so this is going to be our setting. We've got a two-variable or multivariable function, and the x and the y. The things that are going to go into the input slots of our multivariable function are themselves going to depend on a variable. All right. So this is so what we're going to want to do is figure out ddt of f is equal to what. All right. That's going to be the chain rule. That's going to be a chain rule problem because this is the picture would be something like this, right? We've got x, y, z, and here's my graph. Let's say. So this is my graph f of x comma y, right? But I've also got t here. So this is, let's say 0. This is t. And we've got a composition because we're going from the line into the xy plane, right? That's what the x of t and y of t represent, right? It's essentially a vector valued function like we talked about in the previous chapter. Okay, so we think of this, probably the best way to think of this is you've got t representing time. That maps to that defines motion or motion in the plane. So maybe something like this. All right. So perhaps if I do t positive direction like that, maybe I'm going in t positive direction there. Okay. So this is entirely in the xy plane. And then what we do is we're plugging in those values into our function f. So now we're going up until we hit the graph of the f. And then whatever we hit on the graph, that's going to give me ultimately my final value of this composition function f. Okay. So let me write down. This is like my r of t, right? And again, r of t goes to a curve, and then from the curve, because it's a curve in a plane, right? Every point on that curve has coordinates, right? X of t comma y of t, and then we're plugging those coordinates into f, into our function f, and getting a certain output. Okay, so that's our composition function, and ultimately we could write it like f of x of t comma y of t. Okay, so when I write ddt of f equals what I mean is, more precisely, is ddt of this function right here is equal to what? Okay. All right, now the important thing to notice is I'm using straight d's here because this is one variable calculus, right? This is a single variable function. All right, so this calculation is, in a way, just single variable calculus. Okay, so we've kind of reduced a problem from multivariable calculus into a single variable calculus problem. Now, that's great, theoretically, but how do we actually calculate the derivative, right? Well, we use the idea we talked about last time in the last lecture. So we said last time that if we're interested in what's going on at a particular point, a comma b, then what we would do is we would look at the tangent plane at a comma b to our function f, And anything that has to do with derivatives of f or the change in f, we can kind of ignore f and look at the formula for the tangent plane instead. All right, and that formula for the tangent plane is super, super simple. So calculations are actually extremely doable. All right, so let's actually do that right now. So let's do this in the abstract, and then I'll do a actual example. So we have f of x comma y again. We have x depending on t. We have y depending on t. All right. Let's say we want to calculate. So we want d dt of f of x of t, y of t, right? So this is a composition function. And let's say we want to calculate this at a point t equals t naught, all right? Okay, so how do we actually do the computation? So I said that anything that has to do with derivatives of f, I can replace f with the tangent plane. All right. So which tangent plane? Well, if t is, I'm interested in t equals t naught, right? So if I look at my composition kind of map again, so here's t equals 0. Here's the point of interest, t equals t naught, right? What's happening is this is going to the plane, right? So it's going to down here, actually. Let me do that like this. So this is going to the plane, right? And so I end up with a curve down here. And t naught goes to a particular point over here, right? What is that point? That's going to be x of t naught, y of t naught, right? That's where we are at time t as we travel along this curve in a way, right? If we think of this as motion. Okay, now that's the point we're interested. X of t naught, y of t naught. That's the point where we want to look at the tangent plane. Okay, so I'm not going to draw f. I'm just going to draw the tangent plane. All right. So we want to consider this tangent plane. All right. So we're going to do this, but because I don't want to write down all these x of t's and y of t's all over the place, I'm going to abbreviate this as a comma b. All right. So x of t naught is a. Y of t naught I'm just going to call b. All right. Again, this is just to just so that we don't have kind of too messy looking expressions. All right. So the tangent plane at this point, a comma b. Let me write down the formula we got from the discussion last time. That's going to be L of x comma y. I'm not going to write the AB in the corner down here. Is equal to the derivative of f at AB. I guess I was writing it with the partials last time, but let's use our other notation. F sub x at AB, x minus a, plus f sub y at AB, y minus a, and then plus f of a comma b. Okay, so this was our equation for the tangent plane from the last lecture. And again, notice that the most important thing is that super simple. That's a number. That's a number. That's a number. Oh, no. Sorry. This a is a b right there. X minus a, the a is a number. And the y minus b, the b is a number. So the only thing that's a variable, that are variables in this expression on the right-hand side is the x and the y. Okay, so again, it's a super, super simple function. Again, it's the equivalent of a line, right? And a line is just whatever, mx plus b, a number times x plus another number. Okay, so essentially, the moral of last time was if f is differentiable, then derivatives of f can be just replaced with derivatives of L. All right, so we can look at ddt of f, right, of x of t, y comma of t, right? That's going to be equal to, if f is differentiable, right, ddt of L, x of t, y of t. All right, so this is if f is differentiable. All right, I should just write out the whole word. Which again, we're going to assume for our class. All right, non-differentiable functions are really, really unpleasant to work with. Okay, why did I do this? Well, L is super, super simple, right? We have the formula for L right up here. And so let's just write this out. So d dt of L of x of t, y of t is equal to d dt of f sub x a b, x minus a, plus f sub y a b, y minus b, plus f of ab. All right. And this x and this y, right? We're plugging in x of t, y of t, right? So that x is actually x of t. I probably should have written it like that. This y is y of t. Okay. So when I take this derivative, everything is constant except the x of t and the y of t. So this is actually equal to f sub x a comma b times, and this is just well, f sub x is a constant, right? So when I take this derivative, I'm only going to be differentiating the x. So dx dt, right? Again, that x is actually an x of t, plus f sub y a b, right? Just copying down the constant. And then dy dt, right? The b, when you differentiate that, goes away, right? And then plus 0, because this f of ab is a constant. Okay, it's the point of interest, which is just at a, one single point, so it's a constant. All right, or f of the point of interest is a constant. Okay, that's it. That's the chain rule. Okay, so df dt, right? The composition function, the derivative of the composition function, turns out to be this guy right here. Okay, now let me write it in a slightly different way so that perhaps it's easier to remember. So this is going to be, I'm going to rewrite this as f sub x ab is df dx, and then I'm going to put the ab's later, just so to emphasize a small point here. And then dx dt plus df dy is f sub y, and I should use curly d's there. df dy, and then dy dt. Okay. All right. So I'm going to put in the ABs again in one sec, but the point here is this gives us a way to kind of remember the chain rule in that we can think of, just like in one variable calculus, we can think of the dx's kind of canceling, and we can think of the dy's canceling, and we end up with df dt, which is what we actually wanted to calculate at the very beginning. All right. This is purely a way to remember the chain rule. You're not actually canceling these things because these things are not actually fractions. But it's a really helpful way to help you remember the chain rule. And that's probably how you remembered the chain rule from one variable calculus. Okay, but again, that's just a kind of a mnemonic or method of helping you remember. In reality, right, you're supposed to be plugging in AB here. You're supposed to be plugging in AB here. Okay, and remember, AB is x of t, y of t, right? At t equals t naught. Again, if we're doing this at t equals t naught, I suppose I should actually write, let me fill this in. This should be at t equals t naught, right? If I'm plugging in t equals t naught, I'm interested in what's going on there. That should be t equals t naught. That should be t equals t naught. That should be t equals t naught. This is the most kind of careful version of it, of what we want to compute. And let me make it even more messy, but more precise in a way. So AB, we said, was x of t naught, y of t naught. So let me actually put those in. So this is literally what you would be computing. And this final form, it looks kind of horrible, but it's nice in that everything is in terms of t naught. So that, if you're interested in a particular t naught, you don't have to actually pass to ABs necessarily. right? Especially if you're doing things theoretically, and you only want to think about the t's. So this is dt y t equals t naught. Okay. All right, so that's the chain rule for doing a composition where you're starting out with t, you're going to the plane, and then from the plane you're applying the function f and giving you a number. Okay. All right, and again, let me draw this same picture again, just to emphasize, what's happening kind of physically in a way. Here we have t, right? Here we have t naught. That's the point we're interested in. We're going to the plane first. And then once we're on the plane, we're going upwards to the graph of the function. Let me do this in different color. Right? That gives us, and these guys represent the outputs of my composition function, and we're essentially calculating, right? If we move along this way, right, that moves us along this way, which gives us outputs up there, and we're calculating how those outputs change over time. Okay. All right. Notice one thing here. If we, so we talked about parameterization in the last section, and we talked about parameterizing different kinds of parameterization. So one thing you can think about here is what happens if we have two different parameterizations. So here we're doing one parameterization, and then down here let me do a different parameterization. All right, let me use s as the variable instead of the same curve. All right, so perhaps, for example, t moves like this, right? And then s maybe goes faster, right? So like this, but the notches here are farther apart. So s is moving faster. Okay, so that's actually going to affect the derivative of the composition, of course, right? Because what's happening with s, with the composition in terms of s, or in other words, I should write it df ds of x of s comma y of s as opposed to t, right? What's happening is, because you're moving from here to here faster, right, then that means that the changes here, you're kind of checking your location per unit time farther along the curve. Okay, so that's going to affect the derivative, of course, compared to the derivative over here of ddt f of x of t s of y of t. All right, so that's one thing to notice. The parameterization matters of the curve. Okay, it's going to affect this overall derivative. Why did I want to make this small comment? Well, if you think about this whole concept of doing this composition, we can use the idea to talk about derivatives of f in directions other than x and y, right? That's kind of our motivation from the beginning, from last lecture, right? We wanted to see, I know I have df dx, I know I have df dy, the partial derivatives. What's the derivatives in the other directions? Well, I can actually use parameterization. Let's say I wanted to understand how the function changes at this point, not in the x direction, not in the y direction, but in this in-between direction, right? One thing I can do is I can do a parameterization of this in-between direction, maybe just of this line, right? Just to make it simple. I do a parameterization from here to there, right? And then I do a composition with my function. So if my function is up here, perhaps when I go up, it hits the graph, in a curvy way like that, right? When I do the derivative of this composition, let me call that t. We're doing df dt, again, x of t, the composition function, y of t, right? That's actually going to represent how my function changes as I move along the blue, this blue arrow here, right? For example, if the one variable derivative is negative here, that means that I'm moving the slope, the surface, my surface, the graph up here is kind of sloping downwards as I move along the blue arrow down there. Okay, so I can get information about the derivatives in different directions by parameterizing different directions down here, right? Directions other than x and y. Well, I can do x and y as well, but the other directions are the ones we're kind of interested in. So we're actually going to do this in the next section, 15.5, and that's the directional derivative. And that's exactly what we were looking for from last time. All right, we're not going to talk about it here. This section is mostly focused on chain rule. And we also, when we do this parameterization, we have to be very careful about it because the discussion we just had about different parameterizations tells us that if we do different parameterizations, we'll end up with a different answer, right? So we want to make sure we use a standardized parameterization, and that's going to be the arc length parameterization. Okay. All right, but we'll do that next section. At this moment, we're just doing just finding the derivatives of this. We can just think of it as just trying to find a derivative of a one variable function that's created through this composition. All right. Okay, let me do a concrete example. So let's say f of x comma y equals x squared y cubed. Let's just do something simple. All right, we're doing a composition. So let's say x of t is t to the fourth plus 1, and y of t is 3t minus 4. All right, and we're looking at the composition f of x of t comma y of t, and we want to know how does this composition function change as time passes. All right. Let me actually do this at a particular point. So let me do this at t equals 1. Okay. Just to mirror what we talked about just now with the t equals t naught and ab. So in fact, let me write down what ab is also. So when t is equal to 1, what's x and what's y? So x of 1 is equal to, and we just use the formula up here for x. X of t is t to the fourth plus 1. So x of 1 is 1 to the fourth plus 1, which is just 2. All right. Y of 1 is equal to 3 times 1 minus 4, which is going to be minus 1. Okay, so the AB in our discussion above, right, that was, technically it was x of 1 comma y of 1, and that's going to be 2 comma minus 1. All right, so in terms of a picture, we're going from here, this is t equals 0, here's t equals 1, right? That's our point of interest. We want to know how our function changes there. This is going to, this particular point is going to 2 comma 1. So 1, 2, that's x, that's y, that's z, 1. Right? And we want to know what's going on above this point, how our function changes in a way above this point. Okay. All right, I guess I should even write down what the location of that point is. So this point here is f of 2 comma minus 1. Or that's the y, that's the z coordinate. Let me write down the full coordinates. So this, let me do it down here. So this coordinate is going to be 2 comma minus 1. Uh-oh, minus 1, Yeah, the way I've drawn this is at 1. How are we going to fix this? Yeah, let me fix this. Let me just redo this picture. I'm just going to draw literally the same picture, but in a way that's actually correct. So here, y is -1, x is 1. So we're actually going to that point, right? We're going upstairs to the graph of our function in terms of the picture, right? This point up here where it intersects the graph is the other point of interest, and that was, we said it was 2 minus 1 f of 2 comma minus 1. All right. Okay, and actually we have the formula for f. F is x squared y cubed. So this is actually 2 comma minus 1 comma x squared is 4, y cubed is minus 1. Ah, okay. I guess it should be going down. I don't want to draw it again. So what I'm going to do is I'm going to change this to y to the 6, just so it's a positive number. All right, sorry about that. So x squared is 4, y to the 6 is 1. Oh no. All right. Okay, so in terms of this picture, we know exactly where everything is, right? That point is 2 comma minus 1. This point is 2 comma minus 1 comma 1. All right. So how does the function change there? Well, now we can just write down our chain rule formula. We have all the ingredients in terms of what we're going to be plugging in at the end. We have all the ingredients for that. All right, so ddt at t equals 1, f is equal to partial f partial x at 2 comma minus 1 dx dt at t equals 1 plus df dy at 2 comma minus 1 dy dt at t equals 1. Okay, the rest is just plugging in, right? df dt at 2 comma, df dx at 2 comma minus 1. I guess I should calculate the partials. So df dx is, so f was, where's my f? X squared y to the 6. So let me write that down here just so we can keep track of it. F of x comma y is x squared y to the 6. df dx is 2x y to the 6. df dy is x squared times 6 y to the 5, right? And so df dx at 2 comma minus 1 is going to be 2 times 2, which is 4, times minus 1 to the 6, so that's just 4. df dy at 2 comma minus 1 is going to be 6 times 2 squared, so we got 24 and a negative of that. All right. Okay, dx dt at t equals 1. Oh, I guess I should calculate that, or did we? No, we haven't calculated that. So x of t is t to the 4th plus 1. And y of t was 3t minus 4. Okay. Okay, so we take those derivatives, and this is just one variable calculus, right? Dx dt, dy dt, those are just x of t, y of t, so it's just one variable. So I'm just going to write x prime of t is equal to 4t cubed. Y prime of t is equal to 3, just a constant. Okay, So x prime at 1 is 4. Y prime at 1 is 3. And that's it. We have all the ingredients. Let's see upstairs. So this df dx term turns out to be 4. This dx dt term turns out to be 4. This df dy term was minus 24. And this dy dt term is 3. Okay, so ultimately we get 16 minus 24 times 3, 72. And that's going to be 56. Okay, so what do I know? This function is increasing at t equals 1. All right, so the same kind of results that we got from one variable calculus. Derivative still tells us about rate of change. Okay, so one thing you'll notice is our function, right, ultimately is it's a one variable function because we're doing the composition, but we could actually have computed this in a different way by taking this t to the 4 plus 1, plugging it into x squared, right? Because x, if we do the composition, right, x is t to the 4 plus 1. 3t minus 4, plug that in for the y to the 6, and that just gives us a single variable, right? We only then have t's. So if we do that, then we actually do have a single variable function, and we can just do the whole process with that single variable function, right? So note So note f of x of t, y of t, is actually equal to t to the 4th plus 1 squared times 3t minus 4 to the 6th, right? As just a one variable function. And so you can actually just do ddt of this, right? So ddt of f is just equal to ddt of this guy right here. And this is purely single variable calculus. And if you do this, you're going to end up with exactly the same answer that we got, all right, at t equals 1, okay? So you'll get the same answer. At t equals 1, or at any other value, of course, but we just calculated at t equals 1. So theoretically, you could do the calculation this way, but the chain rule is really useful in that if you're naturally working with this two variable function, then you're frequently going to have calculated df dx and df dy already. And so that already gives you kind of a leg up in terms of the calculations for the chain rule. Okay, and if you also think about it, when we did the chain rule problem, when we did it the chain rule way, it's actually literally the same kind of computations, because the df dx, so when we differentiate this one variable function in here, when you calculate, for example, when you differentiate this term here, you're going to be differentiating the inside, the t to the 4 plus 1. That's equivalent to finding x prime that we did just now. And then you're going to have to differentiate kind of the outside, right, which is the chain rule, the one variable chain rule. And that's differentiating the square, right, something squared. And that was the df dx, the partial f partial x that we calculated upstairs, right? Also, when you calculate this in the one variable manner, this thing, you're going to have to differentiate 3t minus 4. That's y prime, which we did. And then you're going to have to differentiate, something to the 6th power, right? And that was the df dy. So you're literally doing the same computation. So doing it this way, maybe it seems more comfortable or comforting that it's just one variable calculus. Literally, you're not saving any effort, right? And it's better to think natively in two variables at this point when we're working with two variable calculus. Okay, of course, we did this calculation at t equals 1, but you could do this calculation in general at any t, and the whole thing would work just the same, all right? Then your answer down here would be in terms of t. Okay. All right. Let me quickly just do one more example, just to make sure we're all okay with this. So f of x comma y. Let me do something x sine y, just something very simple. X of t equals 4t minus 2. Y of t equals e to the t. All right. And let me look at f of x of t, y of t. D dt, right? What is that? So let me just do this kind of the quick way, right? So this is f sub x, or let me write out the chain rule. So this is df dx, dx dt, plus df dy, dy dt. And so df dx is sine y. Dx dt is derivative of 4t minus 2, which is just 4. Let me put parentheses there. Plus df dy is going to be x cos y. Dy dt is just e to the t. Okay. All right, now it's kind of unsatisfactory to leave it like this because we're working with just a one variable function. So if I did want to convert everything to t's, then I just use my instructions right up here. All right. So x of t is 4t minus 2. So every time we see an x, we replace it with 4t minus 2. Y of t, every time we see it, we replace it with e to the t. So ultimately, if we did want everything in terms of t's, then we would just write sine e to the t times 4 plus 4t minus 2 times cosine of e to the t, and then times e to the t. All right. So once you've done a few of these, the computations go really fast. Okay. One comment here is the chain rule. This chain rule formula, this equality right there, it makes sense because in that we have df dx, dx dt, and a df dy, dy dt. You need to see both of them. You expect to see both of them in the chain rule formulation because, well, x depends on t. So you're going to need to see dx dt somewhere in the formula. Y depends on t. So you expect to see dy dt somewhere in the formula, right? And f depends on x. So you expect to see df dx, and f depends on y. So you expect to see df dy. So all of these guys you expect to see in this formula, right? So if you had just written this down without the df dy, dy dt, it should always look suspicious to you. Okay, so maybe so our book, most books like to do these kind of tree diagrams things. I don't really like them very much, but I do kind of like this kind of diagram. Here's t, right? What depends on t? X and y depends on t. What depends on x and y? F depends on x and y. All right. So ultimately, when you do take the derivative with respect to t, right, of the composition, then you're going to need a derivative dx dt. You're going to need a derivative dy dt, and you're going to need a derivative df dx. You're going to need a derivative df dy. Okay. All right. But if you do want to see kind of a visual representation of the chain rule, kind of like this diagram that I made, take a look at the book. They do it slightly different, but the idea is roughly the same, right? So f ultimately depends on x and y. X and y both depend on t, right? So you expect to see all these derivatives in between, right? So the x prime of t, the y prime of t, the df dx, and the df dy. Okay. In order to get from this t to the f. All right. Okay. Now, let's get more complicated. So our next setting is where we have f. Oh, by the way, literally the same thing, same computations. If I have f of x, y, z, and each of these x depends on x, y, z, depends on t, then literally the same thing. So df dt of x of t, y of t, this composition here, z of t, all right? So this is going to be df dx dx dt plus df dy dy dt plus df dz dz dt. Okay, and however many variables you add to this, you just add plus df d whatever that variable is, d that variable dt. Okay. All right, so very, very straightforward once you're comfortable with, for example, the two variable situation. Okay, and again, remember, right, this one should kind of, in a way, cancel with this. This should cancel with that. This should cancel with that. So you should see df dt, df dt, df dt, right? If you see something else, as opposed to the df dt's, something is wrong with your formulation of the chain rule. Okay, let's get into a more complicated situation. So let's say we have f of x comma y. And instead of x and y depending on t, let's say x depends on two variables. Y depends on two variables. All right. Now the question is, what is df? So if I do the composition, right? So let me draw a picture first. So here, I think the best way to think of this is, again, in terms of composition. So what we're doing is ultimately, u and v are our variables. All right. So I'm going to start just like with t, right? Ultimately, t was our variable in our examples above. So we start with the uv coordinate, right? The right way to think of this is this goes to the xy coordinate, right? And then we're applying our f. All right. So ultimately, so this goes to this is a number here. Okay. So this is a composition, right? Any point here goes to a point there, right? And that point there, you apply f to it. That's going to be your composition function, your overall function, which we would write, right? If we wanted to write it all out, would be f of x of uv, comma y of uv, like that. All right. So let me make this a little more clear. So this goes to here, this goes to there, right? Goes to z. And I guess maybe I should draw a 3D picture, right? So in terms of kind of including the graph of my function. So I would have uv here, and this goes to, the uv actually goes into this plane. It's actually a parameterization of the plane in a way. All right, we'll talk about that in a few weeks. Very, very in depth. So this is x, y, z. And then from here, right, you have the graph of your function. So if a point here goes to a point there, then it goes up. That's ultimately our output. All right. Okay. Oftentimes, we call this going from uv to xy, or maybe this picture up here looks a little better. This is often called a mapping. Right? So in the kind of one variable setting, we talked about motion, but this is more like a mapping. Like literally when you think of maps, that's what's going on, right? So in a map, you have let's say your paper map, right? And it represents somewhere in the real world, right? So every point on a map represents some point on the real world. That's your mapping. That's your function from the UV coordinates to the XY coordinates, which represent somewhere in the real world. And then if you do F, perhaps that represents, something about that real world coordinate, right? Maybe the elevation at that point. So ultimately, in that example, our function ultimately would be where at every input, we get the elevation at the real world location corresponding to that input. Okay. All right. in any case, this is a composition. All right. So it's again naturally a chain rule type problem, because again, chain rule is all about compositions. Okay. So we want to know the derivative ddu, for example, of f of x of uv, y of uv. All right. Okay. So the question is, what is this? Right. And we can also ask, of course, I should use partial derivatives. Right, because ultimately f depends on our final function here depends on two variables, u and v, right? So we should use partial derivatives to represent different differentiation. And we can also ask ddv f of x of uv, y of uv, right? What is that? Okay. All right. Oh, by the way, if you do look at the book, the way they kind of talk about this is not really necessarily in terms of compositions and this idea of a mapping, but rather in terms of dependent and independent variables, where x and y in this setting are not independent variables because they actually depend on u and v, which are considered the independent variables of this problem because they don't depend on anything else. All right. I feel like that often confuses people, but if you're comfortable with that, absolutely fine. All right. And also, I like this kind of composition idea because that's the most mathematical way to think of this. Okay, so the question is, what are these two partial derivatives? And the answer is, we already know. We've already done it because what is this? For example, what is du, the partial u of my function, right? Well, if I wanted to calculate partial with respect to u of any function, right? Not necessarily this composition, right? Of any function that depends on u and v, then I think of v as a constant, right? So that's what we talked about last time when we talked about partial derivatives. So ddu of anything, when I do that calculation, I think of v as a constant. Okay. Well, if I think of v as a constant, then this whole setting here is just like my situation when I did ddt of f of x of t, y of t. In that, there's only one actual moving variable, right? In the examples we did above, t is my actual variable, right? T is the thing that's moving. Well, in this dd partial with respect to u is my only moving variable, right? U is my moving variable, u is my moving variable. V is considered constant, v is considered constant. Okay, so this ddu, this partial u problem is literally the same as the ddt problem. Okay, so the chain rule is exactly the same. So du f of x of uv, y of uv is equal to literally the same formula, except with u in place of t, right? And if v's just hang around, coming along for the ride, they contribute nothing. We don't do anything to them because they're constants as far as ddu is concerned. So this is going to be df dx dx du, oops, dx du plus df dy dy du. Okay, just as above here, this is df dx dx dt plus df dy dy dt. Right? So you can see that the difference between these two formulas, the t and the u formulas, there is no difference. It's just we replaced t with u. Because literally, we just did the same version of the chain rule that we have been doing. All right? V contributes nothing because v is a constant. All right? Okay, and of course, if you want ddv of f of this composition, right? F of u, x of uv, y of uv, right? Again, it's just the chain rule we have been doing, df dx, right? Dx dv, comma df dy, dy dv. Okay, and of course, there is no derivatives with respect to u, right, in either of these two terms, because u is a constant, right? There is no mention of u at all. V is the variable that's moving around. Okay, so in fact, the kind of this more complicated situation where we have x depending on multiple things, u and v, y depending on multiple things, u and v, when we take the derivatives with respect to u and v, there's really no difference. All right, so we already know how to do this kind of more complicated version of the chain rule. Okay. All right, and of course, if we did maybe a more complicated setup, like let's say f is 3 variables, right? F of x, y, z, and let's say each of x, y, z depends on 2 variables, right? This is perfectly legal, right? Y depends on uv, z depends on uv, right? Then we could, again, think of the composition function, f of x of uv, y of uv, z of uv, right? What would df du be? That would be df dx dx du plus df dy du plus df dz du. All right. Okay, so again, no mention of v at all. No derivatives with respect to v. You shouldn't see that at all. And if you do this kind of canceling thing, right, you can see df du, df du, df du, right? You better not see any df dv's or anything crazy like that. Okay. All right. And you can make your life as miserable as you like, right? I could do x depends on not just uv, but I can make x depend on an additional few variables, w and q, right? Y depends on uv, w and q. Z depends on uv, w and q, right? What would the formula for the derivative of f of x of uv, wq, wq here, wq here? It would look exactly the same. All right, because the v, the w, and the q play no role because they're considered constants. All right, so as far as the formula is concerned, they're not used at all, or they don't appear at all. Okay. Let's see. I guess I should do at least one example here. So f of x comma y equals x squared y cubed, right? X of uv equals, let's say, sine of u times v, and y of uv equals e to the u times v, right? Then what's df du? Well, df du is going to be df dx, dx du, plus df dy, dy du. That's going to be df dx, 2x y cubed, dx du, v cosine u, right, differentiating this guy here. And then df dy is going to be x squared times 3y squared. And then dy du is going to be v e to the u. Okay, so these are my kind of individual terms. Okay, and again, this is mixed x and y's, but if you did want to convert everything to u's and v's, there's your instructions right there. All right. Okay. All right, so as I said, all that stuff about the tangent plane led us to these chain rule formulas. But in practice, when you're doing the homework problems, when you're thinking about the chain rule, you don't have to think about the tangent plane. Just in practice, you just use the formulas like this. All right, but behind the scenes, what's really going on is that tangent plane discussion. All right, and again, we didn't waste our time kind of talking about it, even though you're not going to be using it. at the moment for the chain rule at least, because we will be using that discussion for linear approximation, I believe, next week. All right, one more mini topic. And we're all set for this section. Okay, so the last kind of topic is implicit differentiation. So this is a situation where you have, let's say, a two-variable function. And one of the variables depends on the other variable. So remember, implicit differentiation in one-variable calculus, the setting was often something like you have 1 plus xy is equal to x squared, or something like that. And the deal was that y depended on x, right? So this is y of x, actually. So what you wanted to do in some of the problems was perhaps to find y prime of x is equal to what, right? And what you did was you differentiated both sides, remembering that y was actually dependent on x. So here the idea is very similar. Y is dependent on x. So we have a function f of xy, but the way we're going to use this function in practice, perhaps, is that y depends on x. All right? Okay, so ultimately we have actually a one-variable function, f of x comma y of x. All right? So this is actually one variable, right? Because x is my variable, y depends on x. Okay, so for example, if f of x comma y is equal to x plus 2y, right? Y of x is equal to sine of x, then ultimately my function is actually x comma y is equal to x plus 2 sine x. Okay. All right, so this is actually a one variable function, and we want to know d dx of f of x comma y of x. What is this? Okay. And if you wanted to do this particular example that I wrote down up here, you could just convert everything to one variable, right, to the x's, and just differentiate that. All right. But we can also take the point of view of the chain rule and do it kind of in a way natively in terms of two variables with the chain rule. And you might think, well, I hate the chain rule. I'm just always going to do it this way by converting it to a one variable function. You could, but this kind of setup where we have f of xy is a generic function in terms of two variables, and then on top of that you have y dependent on x. You see it a lot in differential equations, in ordinary differential equations. So if you kind of only convert to the one variable situation like we did down here and only work with one variable, you're going to be missing out a lot of the theory of ODEs when you do get to ODEs. Okay, so that's a major application of actually this exact exact situation. Okay, so how do we do this in a way more natively? Well, luckily for us, we already know how to do it. It was the first chain rule that we did. Why? Because we can just rephrase this entire question in terms of a parameterization. So let me actually do it like that. Let me actually do it like that, and then we'll write down kind of a general formula. So let me rephrase this as a parameterization. So I'm doing t. All right. I'm going to go to, just like the first thing we talked about, the first setup we talked about at the beginning of this this lecture. T goes to here. Actually, let me make it more accurate. T goes to here, and then from here you're going up to the graph of the function. All right. So what is this parameterization here to this curvy line? Well, the idea is this curvy line should be y of x. This is y of x. The graph of y of x, let me say it like that. Graph of y of x. All right. And what I'm doing is I want to do a parameterization of the graph of y of x using t. Okay. All right. That's the easiest kind of parameterization to do, right? If you have a graph, y of x, the easiest parameterization is just t comma y of t. Okay. So now we have our parameterization to this graph, right? So, and we also have we can do the composition with our two variable function f. So ultimately, what is the function we're looking at? If we start with t, go to this curve using our parameterization, right? I guess let me write it as r of t equals, and I guess I should do sharp brackets here, just to keep the kind of the notation consistent. That's why I kind of didn't like the vector value function stuff, because it's not as natural in this setting anymore. Okay, anyways, we have t. We have a composition where we start with t. We go to the graph of y of x, and then we go up via f. What is this composition function? Well, it's just f of our parameterization. So x of t, y of t, right? But what is x of t? The instructions here say x of t is just t, right? And y of t is just y of t. So this is f of t comma y of t, right? And the point of this is that this is literally the same thing as the guy we wanted to calculate, all right? So we wanted ddx of f of x, y of x, and what I'm going to calculate is ddt of f of x of t comma y of t, right? And because of this equality right there, it's literally the same as what I wanted originally. Okay? Except my variable name will be t instead of x, but I can just convert all my t's to x's at the very end if I want. All right? Okay, now why did I go through all that trouble? The deal is this ddt of f of x of t, y of t, that's the chain rule that we've been doing since the beginning of today, right? So this is df dx. Sorry, I should do partials here. df dx, dx dt, plus df dy, dy dt. But what is dx dt? Well, we said that this parameterization has x of t equals t, right? And y of t is just whatever it is. It's the y of x, the unknown function, all right? So dx dt is just the derivative of t, which is 1, right? So this is equal to df dx of dt dt, right? Again, because x of t is just equal to t under my parameterization, this parameterization of the graph that I used. Okay, plus df dy, dy dt, right? And dt dt is just 1, so df dx plus df dy, dy dt. Oops, these should all be straight d's because it's just a one variable function. I'm very careful about doing that because it really helps to keep straight your straight d's and your curly d's. It helps you remember which things are one variable things and which things are two variable things, so you don't make kind of silly mistakes. Okay, so what I've done is everything in terms of t, but like we said, I've just calculated literally the derivative f of t, y of t, f of t comma y of t, which is the same as the derivative of f of x comma y of x, just with my variable renamed, right? And so I can just rename my t's into x's, and so f dx is equal to partial f partial x plus partial f partial y, and then dy dt. Sorry, dy dx. That was the whole point of it. Okay. All right, so if you ultimately want dy dx, which is often the case, for example, in the ODE setting, just throw everything to the other side, right? So dy dx is equal to df dx. Oops. And also the straight d's here, right, tell me that I'm doing the derivative of the composition function, right, as opposed to this partial here, where I'm just doing the derivative of f with respect to its first variable, all right? So minus df dx, and then divided by df dy, okay? All right, now in terms of applications, frequently what happens is that it's known that f of x comma y of x is equal to 0. All right. So this is a very common setting you'll see in differential equations, where this guy here is known to be 0. So this left-hand side here is known to be 0. And so, I'm sorry, this is known to be 0. And so, of course, its derivative with respect to x is known to be 0. And so that term right there actually frequently is just irrelevant and goes away. All right. And so ultimately, this formula often turns out to be just negative of the derivative of f with respect to x over the derivative of f with respect to y. Okay. All right, you'll definitely see this, something like this when you get to ODEs. This kind of condition here shows up all over the place. And this is why, I guess this is why we call it implicit differentiation, because in one variable calculus, right, in a similar way, you have a function equals 0, right? X squared y plus y cubed equals 3x squared y, right? And you need to differentiate both sides with respect to x. So if you just throw that to the other side, you get equals 0, right? So you would get x squared y plus y cubed minus 3x squared y equals 0, all right? And then when you differentiate both sides, it's similar to the idea that we just did here. Okay, don't worry too much about implicit differentiation for the moment. You'll see it in the future. When you do see it, they'll do the same computation again, because this formula here, which the book writes down as kind of a special formula, you'll actually use it in pretty important ways in the future. But for us, we're not going to use it too much. I would not memorize it, but probably a good idea to at least make sure you understand how we got to this formula. All right. Okay, so everything at this point is set up so that we can actually talk about very carefully how a function changes as we move in directions other than the x direction and the y direction. We've already kind of alluded to it, and you can, maybe a good idea is to stop now and just think about it, how you would do it, and then compare it to how I do it in the next lecture.